This video focuses on triple integrals and looking at the ways they are similar to the double integration we've been doing and how they differ. So we'll evaluate them and we'll also set them up, which is where most of our focus is going to be. So starting off with evaluating the iterated integral that we've been given. So we have the integral of x plus y plus z in the order dz, dy, dx. So the process doesn't change much compared to double integration. We just have an extra round of integration to complete. So we'll start by integrating with respect to z. So we get the integral from 0 to 3, integral from 0 to 2 of xz plus yz plus 1/2 z squared. Evaluate that from 0 to 1, dy dx. So we get the integral from 0 to 3, integral from 0 to 2 of x plus y plus 1/2 dy dx. Now we integrate with respect to y. So integral from 0 to 3 of xy plus 1/2 y squared plus 1/2 y. Evaluate that from 0 to 2 dx. So integral from 0 to 3 of 2x plus 1/2 times 4 is 2. 1/2 times 2 is 1 dx. So simplifying that, we get 2x plus 3. And now we integrate with respect to x, so x squared plus 3x. Evaluate that from 0 to 3. 9 plus 9 gives us 18. So the value of this iterated integral after we complete 3 rounds of integration is 18. So the process of integrating, not much different in comparison to what we've been doing for all of our double integrals, which is nice. That means it extends pretty easily. So the triple integral of the function f of x, y, z over a region E is defined as the triple integral over the region E of the function f of x, y, z dv. So notice we are now integrating dv as opposed to dA for a double integral. So we're integrating over a volume in 3 space. Now with dv, we can replace that with a few different options. There are 6 orders of integration that we can consider working in Cartesian coordinate system. And that just means our x's, our y's, and our z's. So for dv, we can say dz, dy, dx, like the previous example. We could say dz, dx, dy. We could say dy, dz, dx, dy, dx, dz, dx, dy, dz, or dx, dz, dy. So these are the 6 possible orders that we could set up a triple integral in. So right off the bat, that's going to take more effort on our part. Right? For a double integral, we had 2 choices, dy dx or dx dy. Here there are more. Okay. The ability to change the order is related to Fubini's theorem, the one that we established for double integrals. As far as changing the order, though, we have to be conscious of the bounds of integration. If they're all constants, we can move them around a little bit more fluidly. If they're not, just like for double integrals, we'd have to put some work in. It's not impossible to change the order of integration, but it would just be more effort. Now, as far as the triple integral itself, visualizing the function f of x, y, z can be challenging as the graph is 4-dimensional. So if we build up a single integral represents the area bound by the curve, the double integral represents volume bound by surfaces. So as we extend to a triple integral, as far as a geometric meaning, it doesn't have as much value. It is a hypervolume, so volume in 4 dimensions, but since we can't visualize the surface, it's more difficult for us to wrap our head around. So to give some meaning to our triple integrals and motivate why we would even study them, if the function f of x, y, z is equal to 1, then the triple integral represents the volume of region E. So we can use a triple integral now to find the volume of a solid in 3 space. And if the function is defined as a mass density function, then the triple integral computes the mass of the solid. So these applications that we learned about with double integrals now become the motivation for triple integrals, because we can extend the conversations now to 3 dimensions. Right? We can find the mass of a 3-dimensional solid. Whereas a double integral, it was a 2-dimensional solid we call the lamina. We can find the volume of a 3-dimensional solid. Even though we were able to do it with a double integral, we just now will create another way to do that. These 2 applications we'll look at more in the next video. This video, we're going to focus more on just setting up the triple integrals. So we focus our effort instead on visualizing the domain of integration, which is a solid in 3 dimensions. Okay, so when we're going to set up our bound of integration, we're thinking about a 3-dimensional region that we're integrating over. And that can be challenging. There are 3 main ways of describing domains in Cartesian coordinates that we will consider. So remember, Cartesian is the x, the y, the z form. Okay, so we're going to look at each of the ways. We'll do an example of each as well to really solidify our understanding. Our region E is of type 1. So there are going to be 3 types now. If it lies between 2 continuous functions of x and y, which are z equals u sub 1 of xy and z equals u sub 2 of xy. Just to mention, I know using the variable u can be frustrating. It looks like some of the other variables. I chose that just to stick with notation that most textbooks use, but feel free to change that to whatever letter makes sense in your notes. So in 3 space, so we have x, y, z. We're going to draw the region defined by these 2 z equal surfaces. So in this one, let's say we have some surface that looks like this, and then it goes down, and let's say there's some surface on the bottom that looks like that. There. Okay, so this is the region that we're integrating over. On the top, that's z equals u sub 2 of xy, so that's one of the z equal surfaces. And on the bottom, that's z equals u sub 1 of xy. You can make these look however you want. Really, it's just a picture. And then there's some surface that defines the side of this solid, which is going to be important because then once we have defined the region E, we're going to project it down onto the xy plane. Okay, so right there, that's the projection onto the plane. So the projection, we can think of this as a shadow, right? So, or shadow. And we'll use the letter D to denote the projection of the region onto one of the coordinate planes. In this case, since we were dealing with z equal surfaces, we're projecting onto the xy plane. So the region can be formally defined as the set of all points x, y, z, such that x and y are points in the projection, and z is bound between the 2 surfaces, u sub 1 and u sub 2. Right? Essentially, we're thinking of this vertically, right? So if I drew a line here to here, we're basically thinking of this solid vertically. What's the bottom? What's the top of the solid? And then we project it down to figure out how the sides are defined to create the bounds of integration. So going through this process, we can define the triple integral over the region E of our function, dv, as the double integral over the region D. So we're going to take the double integral of the projection after we integrate first with respect to the 2 surfaces. So going from u sub 1 to u sub 2 of the function f of x, y, z. That innermost integral we're integrating with respect to z. And then the double integral dA. So either dy dx or dx dy. We're not sure because we don't know what the actual projection looks like, but that's how that would finish out. two surfaces in terms of x and y define the innermost bounds. Then the projection or the shadow will help us create the bounds of integration for the double integral that remains. Important note, the innermost integral can have up to two variables in the bounds. So since we're integrating with respect to z, the bounds of integration can have x's and or y's. The middle bound of integration should only ever have one variable, so either y or x, depending on our order of integration. And then the outer bounds should always be constants. That doesn't change from our double integration. Right? We want to get a numeric, a scalar value from this triple integral, and that's only going to happen if those outermost bounds are constants. Okay, so let's look at putting this into an example. So set up an iterated integral that represents the triple integral over the region E of the function f of x, y, z dv, where E is the region bounded by the plane 3x plus 2y plus z equals 6 in the first octant. So from this point forward, we're not going to actually do any integration. We're going to focus our efforts on setting up the bounds of integration, since that's the more challenging part. The integration really just follows from all the work we've done with our double integrals. Okay, so first step is try as best you can to draw the solid in 3 space. So if we draw this plane, the x-intercept would be 2, the y-intercept would be 3, the z-intercept would be 6. So we draw that little triangular portion of the plane that's in the first octant. So that means the solid that we are defining is a tetrahedron. So we go along the coordinate axes, along that triangular portion of the plane, and that's our solid. Now, this particular example, we really could project onto any of the coordinate planes, but we want to treat this like a type 1. So we're defining the solid between two z equal surfaces. So at the top, we're bound by 6 minus 3x minus 2y. And at the bottom, we're bound by z equals 0. So those are the two z equal surfaces that define the solid. And then we need to think about what the shadow is going to look like in the xy plane. Okay, so essentially, let's use a different color. We're looking for what that looks like. So now we can go to the xy plane. So that's why I included a two-dimensional axis here. So the x-intercept is 2, y-intercept is 3. So the region in the xy plane is a triangle. And we can define this as either a type 1 or type 2, going back to our double integration regions. And that could get confusing because now I'm using type 1 and type 2 for a two-dimensional region, and we just use it for a three-dimensional region. So we can define this vertically. The equation of that line would be 3x plus 2y equals 6, which means y equals 3 minus 3 halves x. Okay, so with all of this information and these pictures, do the best you can, doesn't have to be perfect, we can set up our triple integral. So triple integral of f of x, y, z. So we're going dz first. So z goes from 0 to 6 minus 3x minus 2y. Just make sure I got those values right. Good. And then when we looked at the two-dimensional shadow, or the projection, we decided to go dy dx as our order of integration. So we're going from 0 to 3 minus 3 halves x. And then x goes from 0 to 2, left to right. So there's the bounds of integration for this particular example. Okay. We define the z equal surfaces. That starts our innermost bounds. Then we look at the shadow. The shadow helps us define the bounds of the outer double integral. So next, our region E is of type 2. If it lies between two continuous functions of y and z, namely x equals u sub 1 of yz and x equals u sub 2 of yz. So notice I've changed the orientation of the axes now, so let's make sure we label them. So x now goes to the left, y comes out, and z goes up. So we're defining in terms of two x-equal surfaces. So let's imagine we had like a paraboloid here and a paraboloid there. So here we just have two surfaces that wind up intersecting each other, and we're looking at the region defined by both of those solids put together. So this is x equals u sub 1 of yz, and here we have x equals u sub 2 of yz. Now we're going to project that. So this is our region E. We project that onto the YZ plane. It would look circular. So that's our shadow, which we'll label as D. So in this case, to figure out what this shadow looks like, we would need to find the intersection of the two surfaces that define E. The region can be formally defined as the points x, y, z, such that the points y, z are in the projection, and x is bound between the surfaces u sub 1 and u sub 2. And that would lead us to our triple integral, which would be the double integral over the region D, single integral between the two surfaces, so u sub 1 of yz, u sub 2 of yz, of our function f of x, y, z, dx now, since they're x-equal surfaces, dA. Same thing as before, the inner bounds can have two variables, middle bound 1, outer bound constants. So looking at an example of a type 2, so set up an iterated integral that represents the triple integral over the region E, function f of x, y, z, dv, where E is the region bounded by x equals y squared plus z squared and x equals 4. So we now have an elliptic paraboloid and a plane that define the region. So labeling our axes, so x, y, z. So the elliptic paraboloid x equals y squared plus z squared is going to go around the x-axis. It's going to go out like this. And then we're going to cut it with the plane x equals 4. So essentially we'd have a plane, and they would intersect in that circle. Right? So there's our region. So I'll use the blue marker just to really exemplify. That's the region E. Okay, so here we have x equals 4, defining that disk that closes the region. And at the bottom, we have the elliptic paraboloid, x equals y squared plus z squared. Again, drawings don't have to be perfect, but the better you're drawing, at least spatially, the easier time you're going to have figuring out your bounds of integration. And now we're projecting onto the YZ plane, and we're going to project that circle, that intersection. So that's going to be the intersection. So that's going to be 4 equals y squared plus z squared. So the intersection of the two surfaces is 4 equals y squared plus z squared. So we have a circle of radius 2. Now, if our projection was circular, most of the time we would go to polar for that double integral. But let's try to do it in terms of x, y's, and z's here. Going to polar is moving us a little bit forward into what we're going to call cylindrical coordinates. So we'll hold off on that for now. So let's treat this as a type 1 two-dimensional region. So that means the upper half of the circle is z equals the square root of 4 minus y squared. And then the lower half would be z equals negative square root of 4 minus y squared. And all of these combined will give us our bounds of integration. So we have f of x, y, z dx. So on the bottom of this region, which is hard to think about bottom, but the closer to the YZ plane would be the paraboloid, so y squared plus z squared. And then further away, the top of the region would be 4. And then we're going from negative square root of 4 minus y squared to positive square root of 4 minus y squared. And then left to right, we're going from negative 2 to 2. And finishing out, that's dz dy. Always pay attention to the plane that we're operating in. Okay, so this is a type 2 example. X equals surfaces, project onto the YZ plane. On the YZ plane, we figure out the bounds for the outer double integral. And the last case is of type 3 if it lies between two continuous functions of x and z. So y equals u sub 1 of xz and y equals u sub 2 of xz. So we have x, y, and z. So here we're projecting onto the xz plane. So let's imagine that we had some surface, let's say it looked like this, and then looked like that, so kind of like a capsule. That's our region E. So up at the top, we have y equals u sub 2 of xz. At the bottom, y equals u sub 1 of xz. Think closer and further away from the xz plane. That's our region E. We're projecting that onto the xz plane. So the projection or the shadow would be a circle. We'll label that D. So then for this last case, formally, it'll be the set of all points x, y, z, such that x and z are in that shadow, and y is bound between the surfaces u sub 1 and u sub 2. And again, in this case, the two surfaces don't intersect. We have another surface that's going to define this shadow. Right? So different potential setups, just to kind of have in our notes. So the triple integral over the region E of the function dv. So we go double integral of d, or over d, of the integral going from u sub 1 of xz to u sub 2 of xz of the function f of x, y, z. Now we're going dy and then dA. So y is bound between two functions of x and z. We project that onto the xz plane. That will help us find the outer double integral bounds. So looking at an example of this case, same triple integral that we've been working with. Now E is the region bounded by x squared plus z squared equals 1, x plus y equals 2, and y equals 1. So now we have three surfaces to consider. So we have x, y, and z. Okay, so we have x squared plus y squared equals 1, which is a cylinder that goes around the y-axis, like that. And draw lightly, because we're going to have three surfaces, and then we'll have to figure out how they intersect. Then we have y equals 1, so that's the plane here. So that's going to start us off in a circle. And then x plus y equals 2, so 2, 2. So we have another plane that's going to cut the cylinder on a diagonal. So something like this. So if I take a different color, I'll stick with blue the way I've been using it. The solid itself is this truncated cylinder that starts at y equals 1 and goes till it hits the plane x plus y equals 2. So up here, that's x plus y equals 2. Now we want it as a y equals surface, so y equals 2 minus x. At the bottom, we have y equals 1. And understandable, this sketch could get a little bit complicated with all the things we drew, so feel free to erase things as they become less useful. Whatever strategy helps you get a decent picture here. So this is the solid E that we're integrating, we're projecting onto the xz plane, and that shadow isn't going to be defined by the intersection of surfaces. It's going to be defined by the side surface, we'll call it, which is the cylinder. So here, that shadow is just going to be the circle of radius 1. And again, we can do it as a type 2 two-dimensional region, but let's just stick with type 1. I don't think there's any disadvantage there. So the top half of this circle is z equals the square root of 1 minus x squared. The bottom, z equals negative square root of 1 minus x squared. So now we set up our triple integral. Give myself a little more space than the last example. Okay, so we're going dy first. So the y surfaces that define this solid, the closer one to the xy plane is 1, and further away we have 2 minus x. And then when we look at the shadow, we decided to define it dz dx. So from negative square root of 1 minus x squared to positive square root of 1 minus x squared. And left to right, we're going negative 1 to 1. Okay, so this is the example of a type 3 region. How it's defined by y equals surfaces and the projection. So right off the bat, as similar as triple integrals are to double integrals, this whole process is definitely more complicated because we're not just working in one of the coordinate planes. We could project onto the xy, the yz, or the xz plane for our projection, and that's going to be based on how the surfaces define our solid. So to help us out, first thing, always try to visualize or draw the region of integration. It's not always the easiest thing to do. Some of these regions can get complicated, but even if it's an okay drawing, it could help set up our bounds. Decide the innermost variable, so essentially what surfaces are defining the solid. Look for a variable that appears twice in the boundary surfaces. Right? If you have 2z equals, that's a good sign. Note that a squared variable might count as 2. So if you had something as a sphere, we would break it in half to the upper hemisphere and the lower hemisphere. And that would give us a plus or minus if we solve for, let's say, z, which now creates two equations. Draw the projection or the shadow on one of the coordinate planes. And this may require finding the intersection of boundary surfaces. So we saw the one example where we had to find the intersection of the plane and the paraboloid to figure out what our shadow looked like. And then use previous techniques to set up the double integral over d. So once we're down into the coordinate plane, now all of our double integration techniques come into play. So one last example that I want you to try. So set up the triple integral of the function where E is the region bounded by the cylinder y equals x squared, the plane y plus z equals 1, and the xy plane. And the nice thing about this example is it can be projected into any of the coordinate planes. So you have some flexibility. I want you to try it. I'm going to write up all three ways. So when you play the video, find the part that looks like the one that you did. Okay, so the first one, treating it as a type 1, projecting the xy plane. This is the region of integration. Should be this wedge shape. Hopefully your drawing looks something like that. Projecting onto the xy plane, we have y equals x squared, and the intersection between two surfaces, y equals 1. So there's our region. So our triple integral of the function, dz dy dx, we're going from 0 to 1 minus y. So those are the two z equals surfaces, the bottom and the top. And then the double integral going from x squared to 1, negative 1 to 1. As a type 2 region, we're projecting onto the xz plane, so defining them in terms of y equals surfaces. Notice the intersection between two of these surfaces, y equals x squared and y plus z equals 1, gives us x squared plus z equals 1, z equals 1 minus x squared. So that's what the projection or the shadow is going to look like. The other is z equals 0. So we set up our triple integral dy dz dx now. So y closest to the xz plane is defined by x squared. Farther away, it's defined by the plane, 1 minus z. Let's get rid of that stray mark. And then In the xz plane, we're going from 0 to 1 minus x squared, from -1 to 1. And then as a type 3 region, same little wedge, project onto the yz plane. It's this triangular region. And we have now triple integral dx, dz, dy. So between x equals surfaces, so this is where it gets a little tricky, only one of the surfaces had an x in it. So you can see in green, I had to solve for x. You get plus or minus the square root of y, and that creates two different surfaces. The front one closest to us and the one further back. So x goes from negative square root of y to the positive square root of y. Right? And that's what we spoke about earlier. And then 0 to 1 minus y, 0 to 1 in the yz plane. So these are good to look back to as well. You might have done this only one way, but you can always try the other two ways at a later point and rewatch this part of the video. This would also lead to questions that ask you to set up all 6 orders of integration. You would take these 3 examples and then just have to change the double integral. So in this one, instead of going dz dy, go dy dz, and that would give you 2 of the 6 orders of integration. So the conversation definitely focused on setting up the bounds of integration, the process of going through all of that, trying to sketch the region as best we can, projecting down the shadow, and then setting up our bounds. So practice with this. It is new. It is not easy, but the more you practice, the more it'll make sense. And then you'll also incorporate actual evaluating problems with this as well.